So, here we are again, and I welcome you all to this second video dedicated to the catalytic reformer. In the first part, we focused on the properties of the feeds and the properties of the gasoline. In the second part, we will be looking at the actual process of the reformer. Once the total naphtha has been hydrotreated and separated into light naphtha and heavy naphtha, we have a 75-145 degrees C cut with a density of between 730 and 770 kg per cubic meter, and a run that varies between 40 and 65. So, let's see what a catalytic reformer actually looks like. First of all, we start to increase the temperature of the feed with a centrifugal pump. Then we increase the temperature in the heat exchangers. While the temperature is increasing, the feed is gradually vaporized. Finally, the temperature is increased to the final reaction temperature in a fire heater before going in the first reactor where the reactions of catalytic reforming will take place. Note that these reactions will take place entirely in the gaseous phase. The pressure ranges typically between 5 and 50 bars and the temperature between 450 and 550 degrees C. So, what exactly happens in the first reactor? We'll be seeing that in a minute. At the outlet of the first reactor, the feed is heated to continue the slower and most difficult reactions. The operation is then repeated in the third reactor. A classic catalytic reformer usually has 3 or 4 reactors. Once the feed has reacted, it is cooled down in the same heat exchangers that were used to heat the feed, and finally in an air cooler before separating the gas phase from the liquid phase in the reactor effluent. Later, we will see what we do with the gas and the liquid. We are now going to have a closer look at the reactions that occur in the various reactors. The first reaction to take place is the dehydrogenation of the naphthenes. This reaction involves a naphthene that will convert into an aromatic. During the process, 3 hydrogen molecules are produced when a cycle is dehydrogenated. This is the main reaction of the process. This reaction is very fast and also highly endothermic. This means that as it is occurring, the temperature inside the reactor decreases significantly. In fact, this reaction requires a significant amount of energy. As an example, in the first reactor, up to 70 or 80 degrees can be lost, which obviously means that the effluent leaving the first reactor has to be reheated in order for the reforming reactions to continue. This reaction is enhanced when the temperature is very high and the pressure low. It has the advantage of producing hydrogen. We will be seeing that hydrogen is used in the refinery for other applications and makes a very significant contribution to increasing the octane number. For example, when a molecule of methylcyclohexane is transformed into toluene, as shown on the screen, the run increases from 75 to 120, which means plus 45 points. However, this reaction means a reduction in volume. Let me explain. The molecules produced during these reactions have greater density than the molecules present in the heavy naphtha. For example, when the methylcyclohexane is transformed into toluene, the density increases. In short, 1 kilogram of liquid methylcyclohexane, which represents 1.31 liters at 15 degrees C, will be dehydrogenated into 0.938 kilogram of toluene, which represents 1.08 liters at 15 degrees C. Therefore, there is a reduction in volume of 18% for this reaction. This is due to the reduction in the mass of the product, because 3 molecules of hydrogen are produced, and to the density effect. I'm afraid that is the price we have to pay in order to increase the octane of the naphthenes. Their mass and their volume are reduced. The second major category of reactions that occur in the reactor is the dehydrocyclization of paraffins. This consists in cyclizing the paraffins and dehydrogenating them at the same time to produce aromatics. These reactions are extremely slow and require very severe temperature conditions. They are also highly endothermic, just like the naphtha dehydrogenation reactions. These reactions are also enhanced at very high temperatures and low pressures. They make a very significant contribution to increasing the octane number and in the production of hydrogen. For example, N-heptane has a run of 0 that goes up to 120 when it is transformed into toluene. That's plus 120 points. These reactions also mean a reduction in the volume. For example, 1 kilogram of liquid N-heptane, which represents 146 liters at 15 degrees C, will be dehydrocyclized into 0.92 kilograms of toluene, which represents 1.06 liters at 15 degrees C. This is a reduction in volume of approximately 27%. Again, like the previous reaction, this is through reduction of mass and density effect. If you remember the diagram showing the distribution in paraffins, naphthins and aromatics in the previous video, with these first two reactions, we undertook the transformation of a large part of the low octane number molecules. But this is only the beginning.